So I will continue with the problems. Um, Before that, so there were some errors in the last lecture. Um, uh, I corrected them, and also I think while talking about this network, there was no error, but some concepts were not. I mean, I was myself not satisfied with the explanation, so I put in the proper definitions and so on. In the notes, some of you may have noticed it. If you haven't, go look at the notes that I put up in the Moodle. And also, I have given a second assignment. Um, yeah, just now I noticed in the email that some of you have asked for extension. I really don't like to give extension. Okay, but just this once, I will extend the deadline. Yeah, so you will see that announced later. Okay, so I want to continue with the problems involving these notions you have been studying, like yeah, indicator functions and matchings. So in that section, there are some problems, some very interesting ones. I will discuss a few of them. Okay. Um, Yeah, but let me say why I don't feel like extending the deadline, because there are only four problems. It's just a very short assignment. And at least one of them I have already discussed in the class insofar as computing the mean is concerned. I just wanted you to do the complete the exercise by calculating also the variance. So problems are not very difficult, but at the same time you need to spend some time doing probability theory also on a daily basis, whether or not there is lecture. So yeah, and this is only the second assignment. If I just keep on postponing, um, you know, there will be fewer assignments than I had intended to give. Okay. So anyway, this time I will consider your request and do something. All right. So now consider this problem. Hmm, there are two n people. Let me use blue color. People forming n couples. Okay. And m people are chosen at random. M, yeah, m people are chosen at random. Find the mean number of number of couples in the remaining 2n minus 1, 2n minus m. Understand? Actually, the book says there are n couples and then m people are dead, and then find the number of surviving couples, mean of the number of surviving couples. But I don't like to say m people are dead. Why use such violent language? Even in language, we can be a little more peaceful. Huh? Yeah. Yeah, these are very difficult times. What is happening in Ukraine? I feel terrible, but anyway, let's carry on. This is all we can do. We can try and understand mathematics. We cannot solve world problems. Okay, so how to do this? Uh, so let um, xi be the random variable. Okay, indicator random variable. Mm, yeah, okay, random variable. Uh, so corresponding to, corresponding to the indicator function. So this is the mass function. So if you like, it mass function. I sub I, bad notation. So this is the indicator function. Function that the ith couple, ith couple. Survive. That is, or in the remaining 2n minus m tuple. Okay. Then what exactly is the required thing? So let s is equal to x1 plus blah 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 plus x n. So you see, when you have a subset uh, of this m, okay, so that subset you can stick in and that will be evaluated in here. So when that subset contains a couple, it contributes this ith couple, then xi will contribute 0. And when they are not in that chosen m tuple, then even one of them. So you see the couple remaining in here means in the subset that you have chosen, um, neither of the two people in that ith couple belong to that subset. So this counts actually. Then this S is the, so what is then we need to compute mean of S, okay, expectation of S. Of course, expectation of S is equal to summation expectation of xi and expectation of xi. Well, this is an indicator function, so this is same thing as probability that of the event. So let us call this thing the indicator function. This is the this event we will call it AI. Okay? So AI is the event that ith couple are in 2n minus m people or among these people. Okay. All right. So we understand. Now this is easy to compute. I mean, of course, all these are the same. Okay, is also the same because the people m subset m element subset is chosen at random. It really doesn't matter. This is same as A1. So you have singled out one couple, okay, and there are two sets, uh, two and many elements in that set. So these two are out, and in the remaining, this m must come from remaining 2m minus 2n minus 2. So probability of that happening is 2n minus 2 choose m divided by 2n minus 2n choose m, choose m. Therefore, expectation of S, this is the required expectation, is so sum over all of these, there are n terms, n times 2n minus 2 choose m divided by 2n choose m. And one can simplify this. I will not do that. Yeah. Hmm. Let us do some more problem. This is an interesting problem. Next one. And this problem seems to have been around for quite a long time. It is due to Daniel Bernoulli. The year is given some 1782 or something. The next one is also due to him. So let's see. Let me explain. The problem is as follows. There are two urns. Urn R and urn blue. Each containing, okay, containing, not each, but containing uh, n red balls and n, same number, n blue balls. So n is not written properly. Same number. In an experiment, you just take out one ball from urn R, one from B, and then exchange. Okay? And you keep doing this k times. So after some time, the composition will have changed. Okay? It may have changed, most likely. Now the question is, so the in a for time t equals 1, 2, 3, blah blah blah, k units, k, a ball from urn R and a ball from urn B, urn B are drawn and swapped. Okay. After k, after k such transfers, what's the probability? Probability that urn R has n red balls. Okay, so we are going to say the balls are numbered. I'm going to say that here. I should have said that at the beginning. I want to say that. So assume that. I suppose it really doesn't matter. Assume that balls are numbered.
So just to be sure, urn R has n red balls and urn B has n blue balls, right?
Absolutely.
Okay.
Absolutely. Okay. So this is actually it really doesn't matter whether the balls are numbered or not. The question makes perfect sense, and it makes no difference. At each time you just choose a ball from each urn and then exchange it. Okay. So after some k such operations, the compositions may be changed. Of course, you expect. The question is, what is the probability that urn R has n red balls after k such transfers? Okay, so Let me move. So this I want to discuss this. Uh, yeah. So the thing is, you see, it's convenient to number these balls, which is what I have done. So let us just before I proceed to give you the answer. So this is my urn and red. I should have known. This is R and this is B. Now you take a typical ith ball, okay, ball labeled I, okay, and now it may have been picked or it may not have been picked, and if it is picked, so you see the thing is after K such transfers, okay, whatever ball has moved, you wanted them to be back in an R. Of course, that automatically means that blue must be back in blue. But once you ensure that whatever ball that came out of R is moved back to R, that's all that matters. Okay. All right. So that means that if you take any ith ball, hmm, AI, ith ball, should make so it may go here, come back here, go here. But if it makes odd number of, if it was picked a odd number of times, then it will be in blue, and you don't want that. You want each one of them to make even number of transfers, if at all. Okay, so that is the main idea and how to implement that. Okay, so I define this random variable. I'm not sure this is the shortest way of doing things, but this is the way I understand it. So xi uh, is the random variable. Mm, yeah, xi is xi is defined as follows. So this is for the given transfer. Okay, so is 1 or minus 1. When is it 1? If ith ball is back in on R. So you see, you may have to just to say this label these transfers just so that xi is not just a number, but it is a random variable. Okay, back in R after operation omega, operation omega. Okay, and this is not in an R. Ith red ball, that's important. An R after omega, operation omega. So this
So,
whole thing I
so
just
what do
call
you
it,
mean by Operation Omega here?
yeah. So this whole thing I call instead of transfer, okay, you can call it transfers. After K such transfers, these transfers, I mean, you may pick ith ball here and then exchange with something jth ball from blue. So like this, no. So you see each operation. So here you may label the things here balls bi. Maybe I should have called it ri here. It doesn't matter. Let me just change it to ri. So a typical operation would be okay. Typical operation. All right. So typical operation. I'm just looking at the um, uh, I, this the operation means that you just perform this operation and keep track of where the ith ball goes. Okay. Let me say this. Explain this. Okay. So uh, when you transfer this, you may have, suppose, let us say, so example, it takes a long time to explain, but it's I think time worth spending. Suppose x is equal to 10, n equals 10, and k is equal to, let us say, 6. Okay. And what you may have done is you may have transfer. So the operation could be you exchange A3 with uh, B4. All right. And then next, this is one one transfer, first transfer. This is omega 1, you may think, and omega 2 involves, so next, you may have picked A10, and here you may have picked B6, or you may have picked next one. Let us do this. So you may have picked, so you see B4 is here, and you may have picked A10. You see, so this is omega 3, and so on. So I didn't want to write all the things. So let us just make this 4 so that to keep it simple. And then one more transfer will be, say, let us say, so you see, we transfer, let us say, B4. B, yeah, B6 is now in red, so B6 is exchanged with A4. Okay, so this is omega 4, and omega is just the 4 tuple. Omega is just omega 1, always a k tuple, omega 1, omega 2, omega 3, omega 4. It keeps track of which balls went which way and their labels. That's it. Okay. Yeah. Hmm. So you need to have this. And now, um, you see, to begin with, you have n balls. And then, so I'm just thinking that I'm removing, uh, yeah, removing one red ball. That means I'm just putting -1 here. And if it is back, then I'm putting +1 here. So this is my reason, or the way I think of the result after k, after you perform an operation. So, or this operation means you know k tuple of transfers, result of k tuple of transfers. Okay, this is what I mean. So I have indicated by means of an example. Okay, now what you need to do is what is the um, yeah, so you are interested that all the balls must be back in red, right? Yeah. So so what is the number of, after you perform a certain operation, let us denote the number of red balls after operation W will be, how many will it be? Okay. So this will be x1 W plus blah 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 plus xn W. But there's a slight problem with this, uh, because I put in minus. No, there's a, so I think it must be, uh, it's not quite this. Let me explain this. This is, yeah, I want to, okay, let me write this as y1 to yn. Okay, let's just write this x1 to xn, not change it, plus n, and I think I should do this divided by 2. Y divide by 2, I think that will become clear in a minute. And here also n by 2. Okay, y this. In other words, to begin with, you had n balls, no? To begin with, you had n balls. So when you so if x1 were to be, x1 of w were to be, that is the first ball labeled 1, if it had gone out after so many transfers, after you perform this operation omega, you are right in subtracting 1 out of it. Uh, Okay, so this requires a little explanation why it is n by 2 and then this. Uh, yeah, I think this will become clear if I had introduced this first. So let yi, this is equal to 1 half plus xi. Then, of course, then rw, r of w is equal to y1w plus ynw. So, you see, you have to begin with n balls. Let us say just perform, let us do this just to understand what is happening. K equals 2. Okay. So after you do this transfer, so K equals 2, so that means it has gone here. One red ball maybe had gone back, and then in exchange you transferred a blue ball. Yeah. And then uh, yeah, well, how can I explain this? Seems um, see, you need to have n there because if let us just say that just if, you can think about it after you do this following special case. See, after k transfers, assume that all the balls have gone there, okay, and without this n by 2 and this one, what would it be? It would be minus n. Without this n by 2 and this divided by 2, it will be minus n because each one of the balls had gone out, and so I put in a minus sign, right? Minus 1. So that would mean that I have minus 1, minus 1, minus 1 everywhere. And of course, you are counting the number of balls. That's not quite right. So what this computes, what this expression says is the change. The xi just computes only the change. Okay, so it should be, whereas if you uh, suppose just one ball had been transferred, then um, one red ball had gone out, and n minus 1 you want to have. So the remaining balls would be uh, yeah. Uh, so the remaining wi's, they will all be 1. That will be n minus 1. But this, because of the presence of minus 1, it would have subtracted one more. Okay. In other words, I am writing, see, let me think this way. Why is it that this is the right one? What is the justification for this? Sorry, that's also by 2 here because, yeah. So you see, if xiw is 1, then this doesn't change. Okay, that ball is very much there. There is no change. Whereas if it is minus 1, then it is yi is 0. Okay, so this, what it says is yi equals yi of w equals 0 if ith ball is gone. Ball is gone out of an R. Okay, and it is 1 if ith ball remains. This is the explanation. This adding, say, dividing by 2 and then adding 1 half doesn't change this, but it changes this to 0. Okay, and that is why this is important. And so you can write like this. Okay, or you can write like this, either way. But it's easier to compute, yeah, the probability of, so probability of this one. Actually, what is the Okay, let me just do this. Probability of, yeah, in fact, what we want is, yeah, xi equals 1. So what we want to compute is not probability that all the things are back. The problem after k-such transfer, this is, what is the problem? Did I write that? Assume that these are the same. I did not write the question. I started talking about this. Find the expected number. Find the mean of red balls. Okay, here I wrote this saying, what is the mean? So I wrote, what is the probability here? Mean number of red balls. Okay, so that's what we want to compute. So this is, and since, any, yeah, ith ball can be chosen, okay, let me say this. This is same thing as, the labeling doesn't matter. So it really doesn't matter. It's the same. XI are all independent. That's the right way to say it. But anyway, so we are interested to compute. We want to compute. Expectation of R. So that's equal to, so expectation of yi and sum over I. And that same thing as n times expectation of y1. But that is same thing as n times. So here is a half. So n by 2, 1 plus expectation of xi, x1, or any one particular thing, doesn't really matter. And this is what we want to compute. So all that boils down to is how to compute expectation of x1 is equal to what? Okay. So now you see, so so you look at the ball and see how keep following its trajectory, okay, and suppose that it is moved back and forth r times, okay, and you keep count of which at which times this was moved, and that is exactly how many things. So yeah, so let me, okay, it's easier for me to write first of all probabilities, or maybe this itself, because it's 1 and minus 1. Summation, let me write this, or okay, choose R, okay, choose R, 1 by n power R, and n minus 1 choose. So okay, n minus 1 by n, choose n minus R, and there's a this with R even, and then minus y minus, because why is it that, okay, let me just write that. So you see you have plus 1 and minus 1. So this is 1 times this, if you like, and minus 1 times. Here, the same expression, 1 by n power r, and r odd here. N minus 1 choose n power n minus r. Sorry, I think this is not r, but this is not n, but k. K minus r. Okay, think about it, why it is. You see, this r keeps track of the times when things are moved. So time t1 maybe it is moved, and then time t3 it was moved back, and so on. Okay, so I just the favorable ones are, that is, when is the first ball back in the earn r, precisely if it is moved r times, and it is not there precisely if it is moved even number of times, odd number of times, and you are computing expectation. So this is what it is. So now let me continue. Sorry, this is getting split into two screens, 2 pages. Anyway, so let me write, but this is easy to compute, right? So this is a summation. And why 1 by n? Because of all the balls, there are n balls, okay? And you want each time, and then you just pick uh, one the ball labeled 1, and probability of that happening out of n balls is 1 by n, and the remaining times other balls are picked. This is the way to think of it. And now this becomes 1 by n, yeah, minus 1 power, okay, I can write here minus 1 power r, okay, choose r, and then 1 by n power r, n minus 1 by n minus 1 by n power k minus r, and that is equal to, and this is sum over all possible things, and that is 1 by n minus n minus 1 by n. I don't know which one goes first. I think yeah, so n minus 1. It computes probability. It has to be like this, whole power k, and which we may write as so 1 minus 2 by n whole power k. Okay. Therefore, now use linearity. Expectation of y1 is equal to, that was a 1/2, just a constant comes out. That's 1/2, 1 plus, sorry, 1 minus 2 by n. I don't know what I do. 1 minus 2 by n whole power k. And therefore, you can plug in and find the answer. I've already done. That's it. Okay. So this is a bit, took some time. I intended to do one more problem. I think I will leave it because it's not much time. I also have to cover some more material. Okay. So we move to the next section. Again, it's all, this whole section is about, chapter is on discrete random variables. But there is, again, it discusses binomial, Poisson, so on and so forth. But one particular lemma I particularly like. So this is not even stated as a lemma, but it's an important observation. So I go to the next one. So see, suppose that um, Yeah, x is a binomial random variable. Let me write here. Should I write? I don't know. X is a binomial random variable n p with parameters n and p. Okay. Now allow n to go to infinity and p to go to 0 such a manner that np goes to lambda. Okay. So let us denote this as x is x and k, x and p, right? So then x and p goes to, so it's not like I'm sending n to infinity independently of p. So it doesn't matter which way n goes to infinity, which way p goes to infinity, but I want np to go to lambda. Lambda is some number bigger than 0. Okay. Then what is this going to? This goes to Poisson with the parameter lambda. This is what we want to prove. So if you like, call it theorem. I like this result quite a bit. Oof. The proof is quite simple, but I think so. Later on, we will see examples, particularly when it comes to continuous distribution. Certain things degenerate into something else, and this is a kind of a precursor to this. So, okay. All right. So, how do we do this? So, what does it mean to say this goes to this? So, let uh, uh, yeah, let us consider probability that, so this x is equal to x and k. Okay, x is equal to k. All right. Now we are going to write this expression. Of course, x is we know this. This is just binomial coefficient, right? N choose k, p power k, q power 1 minus k. So 1 minus p power n minus k. All right. Now take limit. So limit as n goes to infinity, p goes to 0, and np such that np goes to lambda. This is what we should write. It's not okay. P of x equals k. Hopefully, this will turn out, this limit answer will turn out to be something. See, in general, limit even need not exist. So the assertion is that first of all, the limit exists for every value of k, and that gives you a certain discrete, that gives you a certain function, which is actually mass function of a random variable, and that random variable is Poisson. This is what we are claiming. So we just compute the limit. So this is same thing as limit, and I will not write everything. Just write limit and choose k, p power k, 1 minus p power n minus k. And that's equal to, so limit, you write here n choose k as n factorial. Well, let us just simplify that. N times n minus 1 times blah blah blah, n minus k plus 1 divided by k factorial. This is at binomial coefficient, p power k, and this 1 minus p power k, we write it as 1 minus p power minus k times 1 minus p power n. Okay. Now this is equal to, did I do it right? I suppose so. Okay. Yeah, this is okay, no problem. So now you see, as k becomes, k is not a variable here. The limit is not taken over k. K is a finite number. But when n becomes very large, each one of these factors becomes n, or in the limit, it's same thing as n power k. And if you want a very rigorous proof, you just write it as a polynomial in n. Only the leading term matters, and that becomes n power k and k factorial, p power k. Already you see these two conspire to become lambda in the limit. And then, what did I do? Yes, that's right. Yeah, okay, fine, no problem. So this 1 minus p power minus k. So I write this as 1 minus p power k. All right. And 1 minus, now this p, I don't like p because limit as p goes to 0, it's difficult to compute. But write it as np divided by n, that is lambda by n, and then whole power n. Now things are looking good. You see, this is np, I can write limit np is lambda power k by k factorial, and this you have to keep it as such 1 minus p whole power k, and this one, yeah, 1 minus lambda by n whole power n, and this one is already there in Poisson, so I can take it outside of the limit, lambda power k by k factorial. Anyway, it doesn't involve either n or p. And this one, okay, p is some number less than 1. So 1 minus p is some number, again, between 0 and 1. And you raise it to kth power. No, p, sorry, p, the k is fixed. P goes to 0. K is fixed, p goes to 0. Yeah, this goes to 1. Okay, you can say, why not write this as lambda by n, and then here, I mean, like in here. But here, the important point is the exponent is fixed. P is going to 0. No problem. So this goes to 1 in the limit. And this goes to e power minus lambda. And that's exactly P of y is equal to k, where y is Poisson. Poisson distribution, Poisson variable with parameter lambda. This is it. Okay. Yeah, so let me, yeah, there are many more things to talk about, but how much more time? Let's not waste time. I want to start on this following thing. Yeah, I have already discussed discrete in the context of discrete distribution, and also in the general context, actually, joint distribution functions. Do you remember that? Joint distribution, joint okay, joint mass function in the case of discrete random variables, joint mass functions of a pair of discrete random variables. So the important concept that we want to introduce is what is called conditional probability. There will be analog for continuous distributions also, and they will be also extremely important. We are going to study that. But so recall, we studied this. Okay. So in this section, the next section, we want to study conditional distribution condition, yeah, distribution and expectations. So the thing is, context is, as I said, let x1 y be ran. We can do it for many more things instead of just doing it for a pair, but let us understand all these concepts in the context of a pair, be random variables, be discrete random variables with the joint mass function. Yeah, fxy of x comma y. So by definition, I recall for you. So p of x equals x, y equals y is equal to fxy of x comma y. It's a basic definition. Thus, okay. And then what we want to do is conditional. So just like we had conditional probability, you can also have conditional distribution. I suppose it's called conditional. Yeah, okay, conditional distribution. So uh, define. Uh, so the random variable y given x equals x. So when you need to assume that probability of x equals x is not equal to 0 as follows. This is exactly, conditional, like we compute conditional probabilities as follows. Okay, how do we do that? So y of x given x, so you write it in this fashion. So okay, let me write this. So we need to know what is the probability of this is equal to y. We don't write it. This is usually written as probability of y equals y given that x equals x. Okay. So this is, well, I mean, this makes perfect sense, right? So write by is equal to set of all omega in omega. Is at the back of it, this sample space, y of omega is equal to y, which is what we briefly write it as y equals y. Okay, and a of x is same thing, x equals x. So this is exactly probability of by given that ax has occurred. And this is why we needed to know that probability of x equals x is not equal to 0, because then this is same thing as, so then probability of, so this y given x. Okay, so there is a notation for it which I have not yet introduced, but let me do this, continue with this one. This is equal to conditional probability b of y intersected with a of x divided by b of a of x, right? And now what is this? This is equal to exactly probability that x equals x and y equals y divided by probability of a of x. X equals x. We will come to the denominator, but the numerator is easy to write. This is equal to fxy of x comma y divided by probability of x equals x. Now, probability of x equals x can be computed as follows. Mind you, x is a discrete random variable. Probability of this is equal to probability of ay, no? This is equal to probability of union over ay intersect, sorry, ax. What did I do? I should write x here. Intersection by and y is varying. Okay. And now this is equal to, but for distinct values of y, by are all disjoint. And so I have written this as a partition of Ax. So that becomes some probability of Ax intersection by. Sum is over y. Okay. And this is sum over y, fxy of x, comma y. And this is precisely what we write as fx of x, mass function of x. And this is also called marginal okay, of fxy. So it is like you sum over all possible y. It is exactly that anyway. And now substitute this back in there, then what you get is probability of y given x equals x, taking value y, is actually, okay, what is it? Fxy of x comma y divided by fx of x. Okay. Yeah. And sometimes people write this also as, substituting this. So fxy divided by summation over y, fxy of y. Okay, so this, what did I do? So let us, so this y and this y should not be the same. Let me write here some t or something. Otherwise, it will lead to confusion. T fxt. Here it is okay because here x was already fixed. Okay, so now we want to say the following. Yeah, 4:30, still have 15 minutes. Okay, so we denote the mass function of the conditional, mass function of y given x equal to x as f y given x equals x. Okay. I think this is maybe I interchanged x and y, so perhaps this is better written like this: x equals x. Did I fix x or y? I fixed x, I think, throughout. Okay, x. Yeah, I think this is the way to write it. And yeah, y given x equals x. So that fx, so what we have computed is fy given x equals x of y is simply fxy divided by, so fx of x. So here I have written x instead of x comma y, so you understand. That's it. So, okay, this is the conditional random variable y given x equals x. Yeah, and these probabilities are called conditional probabilities, as you already know. And now, one important thing, so I think I should mention this lemma. This is the two variable analog of the unconscious theorem of unconscious statistician. So, theorem of unconscious. I have no understanding why it is called unconscious. So, what is it? So suppose that, so x and y are discrete and variable. I'm not going to write this. So g of xy is a function. Any function. Then I can compute. I can just compose this and get, and yeah, x and y are discrete random variables. Random variables with joint mass function. Mass function fxy. Then see, you can just substitute in the place of x and y, g of x comma y is a discrete random variable. Random variable. And with the expectation, with what is the expectation? Expectation of g of x comma y. Oh, sorry. Capital X, capital Y. Capital X, capital Y is equal to summation gxy fxy. So x comma y, you sum over x and y. That's it. Okay. Is this clear why gxy is a discrete random variable? Yeah. Let me explain. So before we come to the, I'll omit the proof. I think I did the single variable case. Two variable case is exactly the same type of thing, except you keep track of one more variable. That's it. So let us understand what is the meaning of this. So your so you have first of all to begin with omega, okay, and then you have two random variables x and y, and you put them together to get a function of R2, mapping to R2. So given omega, this maps to x omega, y omega, correct? All right. Now you have one more function. This gxy function always means, okay, function means here taking values in real numbers. So g x comma y, I just simply write as g, is a function from R2 to R. Now you see you can compose with the g, and that will map omega to g of x omega, y of g of x omega, comma y omega. So omega goes to g of x omega, y omega. That's first of all a random variable because it associates to each omega something. Yeah, there is something that you need to check. What do you need to check? Okay, that it is actually, yeah, first of all, let us prove that it takes discrete values. So, g by itself may not be discrete values, but omega to this all the way, this composition, because omega, this first coordinate takes only countably many values, second coordinate takes only countably many values, together they take only countably many values. So the image is actually a countably many, a countable set. Now if you take an element in the image set and look at the inverse image, that will be a certain countable set which are already in the image. Okay, I mean, maybe more than countable, it doesn't really matter. But what matters, when you go all the way back, you intersect it with the image of this function, and that's only ultimately is going to matter. When you pull back, that's going to be labeling a collection of events, meaning each one of them will be an event that is an element of script F. Anyway, so we understand that, therefore, this is indeed a discrete random variable. Discrete because although G may assume continuous values, the composition assumes only discrete, only countably many values, and because X and Y are discrete. Okay, so this is a discrete random variable, and we are giving you a formula for computing its expectation. This is an extremely useful formula, and in fact, we have the following. And although I say it in the last 5 minutes, this part of the lecture will be repeated because it's extremely important. Uh, okay, so what did we do just now before I stated this? So we had this random variable y given x equals x. Okay, and now uh, I can, you see, this is a sort of a random variable conditioned on x equals x. Okay, all right. We understand what it is. It is a random variable on the same space omega. As a random variable, I can talk about its expectation. Is depends. See, the moment you take expectation, it's a number, but is a number that depends on x. So denote it by psi of x. Okay. Then I get a function. X goes to psi of x is a function, and it makes sense. It makes sense to talk of psi of capital X. Okay. So this is a very important notion, and this is a new random variable. It's a random variable, again discrete. Okay, and now you see this is really very interesting. You can ask what is the expectation of psi of x? And it turns out that theorem, let me state this theorem, but stop right there. Theorem, yeah. So, okay, so there is a notation for the, okay, see. I'll introduce a notation a little while later, but first expectation of psi of x. Mind you, in order, you see, this of course depends on y also. You see, you had to have this y, so you need to have a pair of random variables. So the answer should depend on y also rather. It depends on both x and y. What is it? It turns out that this is expectation of y. Okay. So, no, sorry, not y, but what is? Yeah, that's correct. Yeah, this is true. Yeah. So this is the. I should have. It's an important result. I don't want to squeeze the proof in the remaining 3-4 minutes, but yeah, let us say this. And there's a notation for, see, this notation psi x is good to understand, but it doesn't bring out the dependence on y. So, notation, I'll talk about it more in the next lecture. Psi of x is denoted as y given x. That's it. Makes sense, right? Because the moment, so you see, the moment you, yeah, I mean, uh, moment you plug in a omega here, what is psi x of omega? This is equal to, by definition, so note. So this is equal to, by definition, this is x of omega. X of omega is just a real number. So it makes sense to say x equal to psi of. So you see, this is, so you think of it as x, that is y given x. See, I had that here, you see. This is what was denoted as psi of x. So in the place of x, I write omega, x omega. So that is why it is written like this, x, y given x. Okay. So I'll stop here for today. And if you have any questions, I can answer that. We still have a couple of minutes. No questions? We'll stop here.